So our
Okay, sir.
says that if you have liquid, you immerse a body inside that liquid will definitely exert some force over the body. Like if you take a bucket, you immersed a glass slab or something in that bucket, then water will push that glass slab or whatever you have immersed with a force, and that force is known as buoyant. Archimedes principle tells how to calculate the magnitude of that buoyant force. So Archimedes principle simply says if you immersed a body in a liquid, say for example, you have a container, it is filled with liquid, it's full with liquid, and you take a body, you immerse this body inside the liquid. So when you immerse the body inside the liquid, liquid will spill. Liquid will spill. How much what volume of liquid will spill? The volume is equal to the volume of the immersed part. If you are immersing, let's say 2 meter cube of the solid, then the liquid that spill, the volume of that liquid would be equal to 2 meter cube. If you immerse 3 meter cube, then it will spill or it will displace 3 meter cube of the liquid. If you can collect all this liquid, you measure the weight of the weight of the liquid is exactly equal to the buoyant force exerted by the liquid on the body. I'm repeating again. Let's take a container, it's full with the liquid. Immerse a body inside the container. When you immerse this body inside the liquid, this body will displace some liquid. Now, since it was initially full, when it displaces some liquid, that liquid will spill. It will come out of the container. If you can collect this liquid, you measure the weight of this displaced liquid. That weight of the displaced liquid is exactly equal to the buoyant force. This is basically Archimedes principle. That Archimedes principle says buoyant force is equal to weight of liquid displaced by immersed part of the body. You don't have to worry about the total volume of the body. You just worry about the immersed volume of the body. Now, I'm just writing this in terms of parameters. Its weight of liquid displaced by immersed part of the body. Immersed part of body. Displaced by the immersed part of the body. Now, what is weight? You know that weight is mass multiplied by acceleration due to gravity. So this is mass of liquid displaced multiplied by g. You can write your mass as the product of volume of liquid displaced, volume of liquid displaced multiplied by the density of liquid multiplied by g. So volume of liquid displaced into density of the liquid into g. This is the formula of buoyant force. You can write one more thing here. Like how much liquid is displaced is equal to the volume of the solid immersion. So you can write that volume of liquid displaced is equal to volume of solid immersed. Both the volumes are equal. Volume of solid immersed. This is the volume of that liquid displaced by the body. So volume of liquid displaced is equal to volume of solid immersed. So here, instead of volume of liquid displaced, you can simply write that buoyant force is volume of solid immersed multiplied by density of liquid multiplied by G. This is the point. So this is the point force acting on the body. This is how we calculate point force. Now, if I say that body is fully immersed, if I say that body is fully immersed, that means volume of liquid displaced, volume of liquid displaced is equal to volume of body, because body is fully immersed. If body is fully immersed, then the volume of liquid displaced would be equal to the volume of the body. So this is Archimedes principle through which you can calculate point force. For an example, so this is water. This is water. Inside water, I place this body. The volume of body inside the water is, let's say, 5 meter cube. The volume of body outside the water, it's 2 meter cube. So the total volume is 7 meter cube. I'm asking you to calculate this buoyant force. So you will write that buoyant force is volume of body immersed, multiplied by the density of liquid multiplied by G. So how much is volume of body immersed? It's 5 meter cube. How much is exactly the density of the liquid? It's water. You should remember that density of water is 1000. G you can take as 9.8 or you can take it as 110. So that comes out to be 5 into 10 raised to the power 4 Newton. This is exactly the buoyant force acting on the body, which is 5 into 10 raised to the power 4 Newton. So this much of buoyant force is acting on the body, 5 into 10 raised power 4 Newton. And this is trying to push this body in the upwards direction. So, okay, next. Decrease in weight of body in a fluid. Say you have a body, the weight of the body is W, which is acting in downwards direction. So I take this pen, the weight of the pen is W, it's acting in downwards direction. If I immerse this body inside a liquid, I immerse this body inside a liquid. I immersed the body inside the liquid. The body inside the liquid. So this liquid will exert some buoyant force on the body. This will exert some buoyant force on the body, and this buoyant force is Fb. Due to this buoyant force, the net weight will decrease because weight is acting in downwards direction, buoyant force is acting in upwards direction. So the apparent weight of body, is equal to weight minus buoyant force. So the decrease in weight of the body is basically this, is equal to buoyant force. So weight will decrease corresponding to buoyant force. If a buoyant force is 2 Newton, then weight will decrease by 2 Newton. This is decrease in weight of the body. Now, if I assume that body is fully immersed, then I can derive some formulas. Those formulas are important for conceptual questions, so I'm going to them. So if we assume that body is fully immersed, that body is fully immersed, if it is fully immersed. So if body is fully immersed, then apparent weight is weight minus buoyant force. See, weight you can write its mass of body multiplied by G. Buoyant force you write as mass of liquid displaced, multiplied by G. So that's apparent weight, mass of body into G minus mass of liquid displaced into G. Mass of body, you can write volume of body multiplied by density of body multiplied by G. Mass of liquid displaced, you can write this as, that's volume of liquid displaced, multiplied by the density of liquid multiplied by G. You can write that volume of liquid displaced is equal to volume of body, because body is fully immersed. If body is fully immersed, since body is fully immersed, so body is fully immersed, that means the volume of body is equal to the volume of liquid displaced. So your apparent weight is this. So this is okay. Sorry. So if I substitute it here, then your apparent weight comes out to be, this is basically conceptual question. The final answer is important. Volume of body into density of body into G minus volume of body into density of liquid into G. I'm representing volume of body by just V. So it's V density of body into G minus volume of body, it's density of liquid. I'm representing it by sigma, density of liquid into G. So instead of rho, I'm using sigma everywhere. Sigma liquid, sigma liquid. Now I'm taking the whole V density of body into G as common. When you take all these terms as common, this is 1. And here you are left with sigma liquid by density of body. I should write it somewhere else. So this is the apparent weight, right? This is the apparent weight. So the apparent weight is, I'm taking V density of body into G as common. So I'm left with 1 minus density of liquid divided by the density of body. This is volume into density of body. It's mass of body multiplied by G. It's actually the weight of the body. This is weight of body. This is weight of body. So you can write that your apparent weight is weight of body into 1 minus density of liquid divided by the density of body. So this is how you can calculate the apparent weight. Apparent weight means if you immerse a body inside a liquid, then the net weight is weight of body minus the buoyant force. That is the apparent weight. So sometimes you can get this expression to derive. This is the derivation of this expression. But remember, while deriving this expression, we have assumed that body is fully immersed. If body is not fully immersed, then you will not get this relation. You will get this relation only if your body is fully immersed. The next is law of flotation. Law of flotation. So if I immerse a body inside a liquid, this is the liquid. It could be a container or it's a river. A body is floating inside the river. Floating means it's neither moving upwards, nor, sorry, it's neither moving downwards nor upwards. If a body is floating, that means it's not experiencing any net force in downwards or in upwards direction. So if you immerse a body inside a solid, inside a liquid, then the force acting on the body is one weight, another is the buoyant force. So one is weight, another is the buoyant force. So in equilibrium, the weight of body should be equal to buoyant force. This is the law of flotation. That a body will float only if its weight is equal to buoyant force. So weight of body is equal to the buoyant force. This is known as the law of flotation. And there are further conditions for a body to float. A body can float. A body can float if, first, either the density of body is equal to the density of liquid, then body can float. Or the density of body is less than the density of liquid. But if the density of body is greater than the density of liquid, then body cannot float, then body will sink. So for flotation, either of the two conditions should match. Either the density of body is less than the density of the liquid, or the density of body is exactly equal to the density of liquid. If either of these conditions are met, then body can float, otherwise it will sink. But tell me one thing, ship is made up of iron. The density of iron is very, very greater than the density of water. But still, ship does not sink, it floats in water. Why? It's basically ship floats because it have air inside, right? It have air inside. Ship is not solid, right? It's hollow. Air is filled inside the ship. And if you take the density, average density of iron, the density of ship is basically the average density of ship is, you can say that this is the density of iron plus density of air divided by 2, which is less than the density of water. That's why ship does not sink, it float. Ship is hollow from inside, it's empty, air is filled into it. But if you make a ship of a solid iron, if you take a solid iron of the shape size of the ship, then it will not float, it will definitely sink. So it floats just because the effective density of ship, which is the density of iron plus density of air divided by 2, is less than the density of water. So this condition gets satisfied and the ship floats. So the question is, density of ice Okay, why the Titanic sank? Why Titanic sank?
Because of iceberg.
Because of iceberg. It's because the guys standing at the top could just watch only the tip of the iceberg. You think that the piece of ice is very small. The ship is very heavy ship. It can crush the ice. But eventually it happens that the iceberg was very, very large. The tip was small. Only the 10% of the tip was visible. The next rest 90% was within the water. So Titanic that collide with this iceberg and it sinks. So it sinks basically because of the fact that whenever ice float in water, 90% of the ice is within the water. Only 10% of its portion is above the water. That we will do, this calculation we will do in this numerical. You will see when ice float in water, only 10% is above the water. The rest 90% is within the water. So in this, it's given that the density of ice is 917 kg per meter cube. What fraction of ice lies below what? The density of seawater is this much. What fraction of iceberg do we see assuming that has the same density as that of ordinary ice? So, so let's say this is the liquid column. In this liquid column, I immerse this iceberg. Okay, this is liquid. And in this liquid, I immersed this iceberg. So this V prime is the volume of iceberg outside the water surface, and this V is the volume of iceberg inside the water surface. Or no, not this one. V is the total volume of the iceberg. So V is total volume of ice. It's total volume of ice. V prime is volume of ice above water. So volume of ice above water. So above water surface, the volume of ice is V prime. So the weight of the piece of ice is W. The buoyant force which is acting over this piece of ice is this buoyant force. So this piece of ice will float. So Sania, which two forces will balance each other if the ice is floating? So which two forces should balance? Weight and buoyant force should balance. See, this ice is floating. Two forces are acting over the ice. One is weight, which is acting in downwards direction. Another is buoyant force, which is acting in upwards direction. So ice can float only if these two forces will keep on balancing each other. So weight of body should be equal to buoyant force. Now I'm writing directly. How much is weight of body? It's volume of ice. So I should write if weight of ice, if weight of ice is equal to buoyant force. Weight of ice is volume of ice multiplied by the density of ice multiplied by G. Buoyant force is volume of liquid displaced. So Sania, what volume of the ice is immersed? This will be V minus V prime. This is the immersed. Yeah, V1 or V prime. Density of water multiplied by G now. So you need this V prime here. So what we can do one thing. We can take V common from here. We basically need the fraction that is V prime by V. So that's V rho ice into G. I'm taking V common from here. When I take V as common, this is 1 minus V prime by V multiplied by the density of water into G. This G will cancel this G. This V will cancel this V. It gets cancelled out. So this is density of ice. This is divided by density of water is 1 minus V prime by V. So from here, you can calculate V prime by V. So you can write that V prime by V is, if you take it to the left hand side, it's 1 minus this term, density of ice divided by density of water. Density of ice divided by the density of water. So V prime by V is, the density of ice is given as 917. The density of water is, I guess, 1024. So if you take LCM, it's 1024 is LCM. It's 1024 minus 917. So this V prime by V is 1024 minus 917. This is 24. And this much is 83. 83 and 24. 83 and 24.
107.
By 102. So if you take the ratio, it's near about 0.1. It's around 0.1. So V prime by V prime is the volume of ice above the water surface. V is the total volume of ice. So you can say that V prime by V is fraction of ice above water surface. Fraction of ice above water surface is V prime by V. I'm repeating again. V prime is the volume of ice above the water surface. V is the total volume of ice. So this V prime by V is fraction of ice above water surface. So the percentage of ice above water surface, V prime by V. To convert this term into fraction percentage, just multiply with 100. So that is 10%. So almost 10% of the ice is above the water surface. The rest 90% is within the water surface. This is what happens with the iceberg. If you look at an iceberg, then only a tip is visible. Only 10% of the portion is visible. The rest of the 90% is within the water surface. Okay, let's move on to the next topic. So this topic is basically Pascal's law. This is the last topic of hydrostatics, means fluid at rest. This chapter is divided into two parts. In one part, your fluid, your liquid is at rest. In another part, your fluid is in motion. So for hydrostatics, that is when fluid is at rest, this is the last topic. Hydrostatics have three major topics. The one is pressure exerted by liquid column. The next is Pascal's law. And the third one is Archimedes principle. These are three major topics in fluid at rest. So Pascal's law, there are number of Pascal's law. Right now I'm discussing Pascal's law of transmission of fluid pressure. I'm discussing Pascal's law of transmission of fluid pressure. Transmission of fluid pressure. So this simply means that if you have so this is container. This container is fully filled with the fluid. This is filled with the fluid. And at every point, let's say this is point A, this point A has some pressure, this point B has some pressure, this point C have some pressure. All points are at different depth, so they have different pressure. At A, let's say your pressure is 10 pascals. At B, let's say this is 8 pascals. Through this example, you will understand that what is the law of transmission of pressure. At C, the pressure is little bit higher. Let's say that is 12 pascals. This is the pressure at every point. Now, I'm increasing the pressure over here. Like I'm pressing this liquid surface with some pressure, and let's say with that pressure of 2 pascals. I increase a pressure of 2 pascals here. Then the Pascal's law of transmission of fluid pressure says this is increase in pressure. It says that this increase in pressure will transmit equally throughout the liquid. Means this point will get 2 pascals pressure. This will get a pressure of 2 pascals. This will also get a pressure of 2 pascals. The net pressure is 12 here, 10 here, 14. This is basically the Pascal's law of transmission of fluid pressure. It says if you increase pressure at a point, then that increase in pressure is distributed equally. Like each point will get same pressure, same increase in pressure. So here the final pressure is 12, here it's 10, here it's 40. This law, so I'm writing the statement of Pascal's law of transmission of pressure. This law tells how pressure can be transmitted, how pressure can be transmitted in a fluid. Pressure can be transmitted in a fluid. This is basically given by the Pascal's law. So there are a number of statements of Saint Pascal's law. The first one is pressure exerted at any point on an enclosed liquid is transmitted equally in all directions. That's the first statement of Pascal's law. The second statement is a similar statement that it can also be stated as a change in pressure. This is basically more technical. A change in pressure applied to an enclosed fluid incompressible fluid is transmitted undiminished to every point of the fluid and the walls of containing vessel. So this is basically Pascal's law. It simply says if you increase from pressure at one point, that increase in pressure is distributed equally throughout the fluid. It's transmitted equally throughout the fluid. That's Pascal's law. Now it's a small law, but it have various applications. The first application is in the brakes, basically. In the car brakes, we use this Pascal's law. Even in the disc brake of bikes, we use this Pascal's law. In hydraulic lifts, lifts which are usually used in car washing showrooms, basically showrooms which wash car, they basically lift car to a height. To lift that car, the lift that they are using, hydraulic lift, is based on Pascal's law. It has a number of applications. So all applications are based on the simple fact that Pascal's law can be used to make force multiply. So this can also be said as experimental verification of Pascal's law. Experimental verification of Pascal's law. Or you can say that this is Pascal's law as a force multiplier. Pascal's law as force multiplier. You can actually build force multipliers using Pascal's law. So see, what are exactly force multipliers? Say I take this system just take this as a container. This have some fluid filled, some liquid filled, liquid or gas. It works on both. So this is some fluid inside this container. It's a hollow container. This fluid is filled. On the container, I put some pistons. I place some pistons here. Some very narrow pistons, some very, very wide pistons. And this is open now. This is open. This is open. This is the piston. Through this piston, you can either push this liquid inwards or this liquid can push this piston outwards. This is piston. This is piston. So it's very clear from the figure that every piston have different area of cross section. For here, the area of cross section is A. For this region, this one, the area of cross section is 2A. For this region, this one, the area of cross section is 3A. So all pistons have different area of cross section. So these are pistons. So I'm pushing this piston inside with a force F. I'm pushing this piston inside with a force F. So piston push inside with force F. With force F. Sania, how much is the pressure? If the area of the piston is A and the force applying on it is F, how much is the pressure?
FA.
Yeah, F by A, ratio of force.
F by A.
So the force which is acting here is F. So pressure is F by A. So when I push this piston inwards, then as Sania says, the pressure in the liquid will increase. So you are increasing the pressure by an amount P1. And according to Pascal's law, that pressure gets transmitted equally throughout the liquid. Means the same pressure get transmitted here. Here also pressure increases by P1. Same pressure will transmitted here. That's P1. So this piston will move outwards. This piston will move outwards due to pressure P1. So over this pressure point, pressure is P1. Area is 2A. Some force must be acting, and I call that force is F2. Sania again. Sania, if pressure is P1 and area is 2A, can you tell me how much is force? Yes, it's P1
into
by 2A.
Into 2A, yeah.
And how much is P1? It's F by A.
F by A.
By
2A.
So this A will cancel this A. And your force, how much is force? 2F.
F
This is the
2F.
magic of Pascal's law. You're applying a force F here, right? You're doing nothing else. You just applied a force F here. When this force reaches over this end, it becomes 2F. So force gets multiplied. It's 2F. So what you did, you take a narrow piston and a wider piston. That's it. You apply some force on the narrow piston, and when this force reaches the wider piston, the force gets multiplied. Pressure remains same, but force gets multiplied. Similarly here, if you want to calculate F3 here, because when you push this liquid inside, this liquid will push this piston outside with the force F3. If you want to calculate this F3, how would you calculate that F3? That F3 will be pressure multiplied by area, which is 3A. So the force F3 will be pressure P1. How much is P1? P1 is F by A. It's F by A multiplied by 3A. So this A will cancel this A, and you will get that your force F3 is exactly equal to 3. So this is F2, which is equal to 2F, and this is equal to F. So using Pascal's law, you can make force multipliers. That force multiplier, as you keep on increasing the area of the piston, the force keep on increasing so that your pressure remains same. If area is 3 times, force is 3 times, if you take the ratio, then it will be, ratio will remain same, pressure will remain same. So this is force multiplier, and this is also the experimental verification of Pascals. So if you calculate pressure here, force is 2F, area is 2A, pressure is F by, here again pressure is F by. If you want to calculate pressure here, force is 3F, area is 3A, pressure is again F by. Pressure will remain same. So the applications of this Pascals, so various applications. Some important applications is first hydraulic brakes. The second one is hydraulic lift. So this hydraulic brakes are not discussed by NCRT, but NCRT have discussed hydraulics or not brakes. NCRT have discussed hydraulic lift in very much detail. So we will do hydraulic lift. I'm not discussing hydraulic brakes now. But the principle is same, the working is same. For both these things, the working is this only. You're applying force to a narrow area of cross section, and you're expecting a larger force at a larger area of cross section. That's it. Now see, what is hydraulic lift? So this is fluid filled. This is one piston here, piston having smaller area of cross section. This is the wider piston. The area of cross section of the smaller piston is, let's say, A1. Of the wider piston, the area of cross section is A2. So let's say you want to lift this car. I place this car on this part, wider area of cross section. And I'm pushing this piston here with piston having smaller area of cross section. I'm pushing this with a force F1. Now you know, when the force will transfer through this fluid and it reach here, the force will get multiplied. If this area A2 is 100 times of A1, then force will get multiplied by 100 times. Pressure will transmitted equally, but force will get multiplied. This is what happened in a hydraulic lift. We put a car here. We push this piston, this narrow piston with a small force. When the small force reach here, it gets multiplied and it can actually lift the car. This is how an hydraulic lift works. Now, in the numericals of hydraulic lift, you're supposed to calculate this F2. So I'm just writing a few points about the hydraulic lift. It is used to lift heavy objects. Used to lift heavy objects. This is based on Pascals law. Heavy objects, this is based on Pascals. A simple application of Pascals law. So I'm just writing that what is F1? F1 is force on smaller area of cross section A1, smaller area of cross section A1. What is F2? F2 is force on wider area of cross section A2, wider area of cross section A2. This is F2. Pressure should transmit equally. Pressure transmitted or pressure transmit equal. So that would mean pressure at the narrow end is equal to pressure at the wider end. So that means pressure at narrow end is equal to pressure at wider end. So at the narrow end, the pressure is F1 by A1. At the wider end, the pressure is F2 by A2. If you want to calculate F2, then you can simply cross multiply here. So F2 is A2. If I take A2 here, so this is A2 by A1 into F1. Now, since A2 is very, very greater than A1, So A2 by A1 is very greater than 1. You're multiplying F1 with someone which is very greater than 1. That simply means that F2 is very greater than F1. So force F2 is very greater than the force F1. This is how a hydraulic lift works. So we apply a very small force here. When this force transmits here, it gets magnified. This is the working of a hydraulic lift. So in a car lift, compressed air exerts force F1 on a small piston having radius of 5 centimeters. So this is basically F1. So piston have radius 5 centimeters. So you can calculate the area of the piston. The area of the piston is just pi into r square. So that's pi. R is 5 into 10 raised to the power minus 2 square. So the area of the piston is just 25 pi into 10 raised to the power minus 4 meters square. This pressure is transmitted to a second piston of radius 15 centimeter. So the area of the wider piston A2 is, it's pi into 15 into, yes Sania, now you are close, 10 raised to the power minus 2 square. So A2 is pi, it's 225 into 10 raised to the power minus 4 meters square. F1 is unknown, but you know F2. What is F2? F2 is the force required to lift this car. So the force required to lift this car is equal to the weight of the car. So the weight of the car is 1350 multiplied by G. So it's 13500 Newton. This is the force required to lift the car. Now you can do one thing. Use this direct relation that F1 by A1 is equal to F2 by A2. From this expression, you need F1. So you can write that your F1 is, it's A1 by A2 into F2. So you can write that your F1 is A1. It's 25 pi into 10 raised to the power minus 4 divided by A2, which is 225 pi into 10 raised power minus 2 multiplied by F2, which is 13500. Pi gets cancelled out with the pi. 10 raised power minus 4 will get cancelled out with this thing. This is 9. If I cancel this is 9500. So your F1 comes out to be 1500 Newton. So the question is very lengthy. You have two syringe. I'm just drawing a diagram, although diagram is not given. So this is, you have two syringe basically. So this is a narrow syringe having narrow area of cross section. Then you have another syringe having comparative wider area of cross section. So this is how these two syringes are connected. So you can take that the diameter here is 1 centimeter. The diameter here is 3 centimeter. Find force exerted on a larger piston when the 10 Newton is applied on the smaller piston. So this complete thing is filled with water. Everywhere you have water. If you look this diagram carefully, then you will realize this is nothing but a force multiplier. So applying some force F1 here. So this will go outside with a force F2. This will move out with a force F2. See, I'm solving part 1. So again, it's F1 by A1. This area is A1. This area is A2. So you will write F1 by A1 is F2 by A2. Say A1, you can write this as A1 is pi r square. But now radius is not given, diameter is given. So you can write that radius as its diameter by 2 whole square. So you can say that area A1 is pi d square by 4. Similarly, you can calculate area A2, that's pi d1 square by 4. It's pi d2 square by 4. So if I substitute A1 here, and if I try to substitute A2 here, then what you will get is it's F1 divided by A1. A1 is pi, it's d1 square by 4. So we can take this 4 in the numerator. This is F2 divided by pi d2 square by 4. It's a numerator. 4 will cancel this 4. Pi will cancel this pi. You're supposed to calculate F2. So F2 will comes out to be F1 d2 square by d1 square. Now let's substitute the values. How much is F1? F1 is 10. How much is D2? D2 is 3 centimeter and D1 is 1 centimeter. 3 centimeter, D1 is 1 centimeter. So F2 comes out to be 90 meters. See, in the second part, saying that if a smaller piston is pushed in through 6 centimeter, how much does the larger piston move out? So you can solve it in this way. This is a smaller piston. You push the smaller piston in through 6 centimeter. Pushing this inwards to 6 centimeter. Then this larger piston will move out. This will move out by some distance x2. You're supposed to calculate this x2. So to this calculate this x2, you can use one logic. If you push this piston inwards, that means you are pushing some liquid inwards. This piston, larger piston will move outwards, means some liquid will get pushed outwards. Some volume will get pushed outwards. You can compare both the volume should be equal because the volume that you are pushing inwards is the one which is getting pushed outwards. So you can solve it using this simple logic that volume of liquid pushed inwards is exactly equal to volume of liquid pushed outwards. Volume of liquid pushed outwards. So the volume of liquid pushed inwards is this area of cross section multiplied by 6 centimeter, and the volume which is pushed outwards is here area of cross section multiplied by x2. So you can write this in this way, A1 into x1, which is equal to A2 into x2. Let's call this as x2 and this as x1. Now you know how much is your A1 and A2. This is your A1 and this is your A2. Let's put this in capital letter. This is A1 x1 and this one is A2 x2. For A1, you can write this as pi d1 square by 4 into x1. Your A2 is pi d2 square by 4 into x2. Pi will cancel this pi, 4 will cancel this 4. So you have d1 square x1 is equal to d2 square x2. Now you can just substitute the values. You can simply substitute the values here. How much is d1? d1 is, now I need x2 now, so your x2 is, it's d1 square by d2 square multiplied by x1. So d1 is 1 centimeter, 1 square. d2 is 3 centimeters, so it's 3 square. x1 is 6 centimeters, so that is x2. So if I calculate this, x2 comes out to be 6 by 9. Your x2 comes out to be 2 by 3. Your x2 comes out to be 0.67 centimeters. So this is how you can calculate actually calculate your x2. Your x2 is 0.67 centimeters.